So welcome everybody to the running seminar of the CRM program on higher homotopical structures. So today's speaker is Amar Hadzihasanovic from Tallinn, who will speak about the smash product of monoidal theories. So please, Amar, go ahead.
I'm gonna share my screen.
Yes, please.
Okay. So yeah, thank you to the organizers and especially to Joachim for inviting me to give this talk. And I'm pleased to be speaking in this seminar because the work that I'm about to present, I think it has some interesting ideas for homotopical algebra. But I've come to it from a slightly different side, from the side of these diagrammatic methods and rewriting bordering theoretical computer science. So I do not have a kind of insider's perspective on homotopical algebra. So I'm going to try to give you an overview of the main ideas of this work, and then I'm going to show several pictures, and my hope is that some of you will see some of it and think, oh, this looks like something that I know, and then they will want to talk to me about it. So first of all, I'll give you some references. So mainly I'm going to be talking about the content of this recent paper that I put in the archive just last month. And the title is the same as the title of the talk. But the technical groundwork is mostly in this other paper from a few months ago, diagrammatic sets and rewriting in weak categories. That's also in the archive. Some of the results that I'm going to state are also really in that paper, not in the new one. So first of all, this talk is about relating two different constructions, one from topology, one from categorical universal algebra. And first of all, I'm going to present what these are quickly. So I'll be talking about props. So if you saw Martin Markel's talk in the first day of the workshop, he spoke about several of these gadgets for presenting generalized algebraic theories, including props. So in this talk, a prop will always be a colored prop. And a succinct definition is that a colored prop is a symmetric, strict monoidal category, a small category in particular, whose objects are freely generated from a set of sorts under the monoidal product. The idea here is that I can see the type of a morphism in a prop as a list of sorts in the input and a list of sorts in the output, which may be empty. And the interpretation that we give to this is that a morphism of this type is an operation with n inputs and m outputs. I'm going to be using string diagrams to represent these operations. So this phi from A1 to AN to B1 to Bm is going to be a node with n incoming wires and m outgoing wires. And these operations can be composed along any number of wires. So by connecting any number of outputs of phi to any number of inputs of psi, including no wires at all, in which case we just juxtapose horizontally the two diagrams. So any kind of arrangement of this type, of this form, has a composite in a prop. And there are some special operations of the symmetric gradings which allow us to permute the wires and connect them in any kind of permuted order. So colored props generalize some of these other gadgets, and in particular, we can identify symmetric colored set operands with the props whose operations decompose into operations with a single output and symmetric ratings. So before somebody asked me, everything in this talk will be non-enriched or set enriched, if you prefer, because the constructions are very combinatorial. I do not have any idea of how any of it could extend to kind of more general V-enriched setting. We can also identify multi-sorted algebraic theories in low V sense, with props that are in particular Cartesian, in the sense that the symmetric monoidal structure is actually a Cartesian monoidal structure. The tensor product is a Cartesian product. If we define a category of props whose morphisms are symmetric monoidal functors that send sorts to either sorts or the unit, this is a slight deviation from what people usually do. Usually they consider functors that only send sorts to other sorts, but it seems quite harmless, and it's useful for technical reasons in this talk. We can identify the categories of symmetric colored operands and the categories of algebraic theories as full subcategories of this category prop. So the idea is that both in the operand case and in the algebraic theory case, it is that really the only non-structural, non-trivial operations are the ones that have a single output. In the operand case, the only other thing that we can do is permute wires, and in the algebraic theory case, the only other thing that we can do is copy or discard some inputs. In this sense, props are more general in that they allow us to also talk about operations that are kind of atomically multi-output. So given a prop, we can consider its models in a symmetric monoidal category, and a model of a prop is just a symmetric monoidal functor from T to M. And we can form a category of models of T and M whose morphisms are monoidal natural transformations. And the fact is that this category itself admits a symmetric monoidal structure. The idea here is that if we have two different models of the same theory, for every operation, we can kind of run the two models in parallel, and then use the symmetric structure to redistribute inputs and outputs, and that give us a new kind of a new model obtained as a composite of the first two. So because we have a symmetric monoidal structure in this category of models, we can take another prop and we can consider models of this prop in the category of models. And then we can define a tensor product of two props as determined universally by requiring that models of the tensor product of T and S in a symmetric model category M correspond naturally to models of S in the category of models of T. Because this is actually going to be a symmetric tensor product, so this is going to also be up to natural isomorphism, the same as models of T and the category of models of S. The tensor product is part of a symmetric monoidal structure and prop. This has been studied by Philip Hackney and Marcy Robertson in a paper from a few years ago, whose monoidal unit is the prop of permutations, the one whose operations with n inputs and n outputs are exactly permutations and then an element set. So I'm not going to show you an explicit definition of what a tensor product is. This is really one of those cases in which the most natural way of understanding the monoidal structure is by seeing what it is left adjoint to. So it's there's a kind of natural, say, space of models inside a symmetric monoidal category, and then we really define this as as a left adjoint to that operation. If we restrict this monoidal structure to the full subcategory of symmetric operads, it is actually closed under this tensor product, and we recover what's known as the Boardman-Vogt tensor product of symmetric operads. If we restrict it to Cartesian props, we recover what is known as the tensor product of algebraic theories. So this operation really generalizes these two in this sense. So even though I'm not going to explicitly define how this tensor product is defined, I'm going to give you some examples. So there is a single sorted prop whose models are monoids. This is in particular one of those that are also come from a symmetric operad. I think I've picked that in homotopy algebra circles, one speaks of the operad of associative algebras rather than the operad of monoids, but those are the same thing. And one can take a prop and one can take its dual by just reversing the direction of morphisms. And then models of its dual in a symmetric model category are just internal comonoids. So now if we take the tensor product of mon with itself, we obtain the theory of commutative monoids. If we take the tensor product of the theory of monoids and the theory of comonoids, we obtain a theory of bialgebras or bimonoids. This is interesting because this is actually a prop which is not either a Cartesian prop or a symmetric operad. If we take the dual of commutative monoids, so this is the theory of commutative comonoids, tensoring any prop with this theory of commutative comonoids gives the free Cartesian prop on T. So this is actually tensoring with commutative comonoids is actually the left adjoint inclusion of Cartesian props into props. Okay, this is all I'm going to say for now about the tensor product of props. So let's talk about the smash product of pointed spaces. So take two pointed topological spaces, and in all this talk, I'm going to be restricting myself to nice topological spaces in the monopy theorist sense. So, for example, compactly generated Hausdorff spaces. Then there's mesh product is obtained by first taking the Cartesian product of these two spaces, and then quotienting the subspace of this Cartesian product obtained by taking the union of all the fibers of the two base the base point of x and the base point of y. And this is part of a well-known symmetric monoidal closed structure on the category of spaces, in this case, the compactly generated Hausdorff spaces, which is whose internal home corresponds to taking the space of pointed continuous maps between a pointed space and another. The model unit is the coproduct of 2 points, where the point is one of the inclusions. So one of the typical examples is that taking the smash product of any space with the circle gives the reduced suspension, and in particular keeping doing smash products of circles just gives the sequence of all the n spheres. So question, why on earth should these two be related? Maybe there is somebody in the audience who's used to these kinds of connections and will just think, well, yeah, I can see that there is an analogy. For me, at least, it is quite surprising. One seems very universal algebraic, almost logical. The other one is very topological. So the goal of the next few slides is going to be to make the idea that these two are connected a bit less far-fetched. And in the first part, I'm going to just speak a lot by analogies, which for now are not supposed to be taken at face value. Later we'll see in which way they can be made precise. So first one observation that, a prop is sometimes seen as embodying this idea of a symmetric monoidal theory as a generalized type of algebraic theory. We can consider even kind of broader generalizations. We consider planar monoidal theories corresponding that are called probes, and we consider braided monoidal theories that are called props. The definition of these is the same as the definition of props, except we cross out symmetric wherever it's said. So these are strict monoidal categories and strict braided monoidal categories. So we can form categories of these things in the same way as we form the category of props. So we get a full subcategory of props in the category of props, and we get a forgetful functor from props to probes, where we just forget that the braidings are structural operations, and we just treat them as morphisms, as operations like all the others. And both these have left adjoints. These are just imposes that all the braidings become symmetric braidings, and this F just freely adds braidings. So the theories of monoids and comonoids that I talked about earlier are naturally branar monoidal theories, in the sense that they can be presented by equations of diagrams that never use the braidings or symmetric braidings. So in particular, the prop of monoids is a free prop on a probe. However, if we take the tensor product, this is no longer a planar monoidal theory. And in particular, the theory of bialgebras contains this equation, which contains in the middle this symmetric braiding, and there is no way to give an equational theory of bialgebras that doesn't use the symmetric structure. So in particular, there is no internal tensor product of probes. And I'm at some point when early in my PhD, I read a paper this paper by Steve Lack on composing props, and he made an observation of this kind, where somehow the bialgebras is obtained by composing theory of monoids and comonoids that do not necessarily have to contain symmetries. But somehow in this equation, which presents a compatibility between the monoid multiplication and the comonoid comultiplication, somehow this symmetry cannot be clearly attributed to either factor. So the only thing that we can really do is kind of consider it part of the background structure of whatever world of universe of theories we are considering. So I spent some time kind of thinking about this equation a few years ago, and at some point I came up with this topological interpretation. So we take the string diagrams that correspond to the monoid multiplication here, and the comonoid comultiplication, and then we kind of extend them in space. So from string diagrams, they become these surface diagrams, but we extend them into perpendicular directions. And then we take these two branching surfaces and we intersect them, and then we kind of slide one past another. So we kind of take one and we slide it towards the bottom, the other one we slide it towards the top. And as kind of one branching passes the other, so it reaches this critical point where one branching slides into the other, the intersection of the two surfaces evolves like this. So we have this shape on the left and this shape on the right. And this kind of, the two pictures are very much like the two sides of the equation of bialgebras. And in fact, in the definition of the tensor product of props, there are exactly all these. One first forms some kind of free prop on the generators of the two factors, and then imposes some compatibility equations. And all these compatibility equations can be given this same kind of surface diagram interpretation. So of course, my question was, what is going on? So the way to think of this is, if you're familiar with this idea of the periodic table of n categories, this was first proposed in a paper of John Byers and James Dole, and then there's been a couple of papers kind of formalizing this idea in low dimension by Eugenia Chang and Nick Gursky. The idea is that a monoidal category may be seen as a kind of loop space inside a bicategory with a single zero cell. But a braided monoidal category can be seen as a twofold loop space of a tricategory with a single zero cell and no non-degenerate one cells. So in particular, through this picture, we can see these kind of planar theories and these braided theories as being presented by diagrams in different dimensions. And if you think about this sliding surfaces picture, it's a way of producing an equation of diagrams in 3D space, so diagrams in a tricategory, and from a pair of planar diagrams, so diagrams in a bicategory. So you see this equation of diagrams in a tricategory, we can see it as a four-dimensional object, and that's obtained from a pair of two-dimensional objects. So one thing that this suggests is that even though we cannot form a tensor product of pros which returns a pro, what we can do is define an external tensor product which takes two pros and returns a prop. And this is compatible with the tensor product of props in this sense that this diagram commutes up to natural isomorphism. So if we take two props that are free on pros and we do their tensor product, it's the same as taking their external product, which returns a prop, and then reflecting it onto a prop. And in a certain sense, this external tensor product is the kind of the real combinatorial core of the tensor product of props. In the sense that we can take two props, we can do the external tensor product of their pros, then we reflect it and we obtain a prop. That's not quite the tensor product of the two props, but it does come with an inclusion, a natural family of inclusions of the factors into their product. And if we impose that these inclusions actually preserve the original symmetric braidings, then we obtain the tensor product of props. So what I'm actually going to be talking about here is not relating the tensor product of props directly to the smash product of spaces, but it's going to be relating this external tensor product to the smash product of spaces. But later, if you don't find this completely satisfying, later I'm going to tell you a nicer way of thinking of the tensor product of props, but that I cannot for now make completely precise. So now, because pros and props are in particular these strict monoidal categories, so we need to not think about this general periodic table, but we need to think about a strict form of this, where a pro can be identified with a two categories, a strict two category with a single zero cell. But a prop has to be identified with a gray category with a single zero cell and no non-degenerate one cells. Gray category is this semi-strict notion of a three-dimensional category that has all the axioms hold strictly except for the interchange axiom. So now, because these objects have a single zero cell, so they're naturally pointed objects. So now I would like you to think of a high category as being like a space of directed cells, kind of in the way that we can see a high groupoid as being a space. So we see a high category as a space of cells that have an orientation. So if we have this kind of topological picture in mind, we can see a pro is the loop space of a pointed directed two type in the sense of monopy theory. And a prob is a twofold loop space of a pointed directed three type. But both these things, though, would apply also to strict monoidal categories and braided strict monoidal categories in general. So what about the fact that these have freely generated objects from a set of sorts? And to interpret this, we're going to take a hint from the theory of polygraphs or computads, where one can see a freely generated strict high category as a polygraph as being like a formal CW complex in the category of strict omega categories, in the sense that it's an object that can be inductively generated by progressively adding cells of increasing dimension. As long as we allow the topological n ball to be modeled by the n globe, so the strict n category which models n cells, and we let the gluing maps be modeled by arbitrary functors from the boundary of the n globe. So while pro or prob are not like entirely freely generated objects, but the one cells of a pro should be freely generated, and the two cells of a prob should be freely generated. So we can see this in the space picture. We can see this as giving a one-dimensional cell complex structure on a subspace of a pro, and a two-dimensional cell complex structure on a subspace of a prob. So if we put together all these chain of analogies, that I would like you to think of a monoidal theory as being like the loop space of a pointer directed space, which is a homotopy 2 type and is equipped with a one-dimensional cell complex structure. And I would like you to think of a braided monoidal theory as being like the twofold loop space of a pointer directed space, which is a 3 type, and has a two-dimensional cell complex structure on a subspace. So if you accept this analogy, then the connection with mesh products should become a little more plausible, because now the sum of the dimensions match. Because if we take a mesh product of two spaces which are loop spaces, we do get a twofold loop space. If you take this mesh product of two one-dimensional cell complexes, we get a two-dimensional cell complex. And if you remember in the surface diagram picture, I said that from two-dimensional cells, we get a four-dimensional object, and actually this mesh product of two cells is a four cell. Importantly, though, it's not true that this mesh products of two types is going to be a 3 type, not at all. And that's actually going to be a good thing. So to make this connection precise, what would we want? We want to have a category of directed spaces together with a monoidal structure from which we can induce this mesh product on a category of pointed directed spaces. We want the categories of pros and probs to embed faithfully into this category of pointed directed spaces. in such a way that this external product of pros will factor through this mesh product. And in addition, to have the kind of a functorial bridge to mesh products, we also want a direction for getting functor from directed space to pointed spaces that sends mesh products in the directed sense to mesh products in the usual sense. And that's what we do get in this paper. So when I started this work, the closest thing to having something like this that I could see was the category of strict omega categories, but not with the Cartesian product, but with the lax gray product. In particular, because a pro can be seen as a two category. However, if we do try to define a gray mesh product of two monoidal categories as pointed two categories, we don't get a braided monoidal category, but we get this thing called commutative monoidal category. So we get a doubly degenerate strict three category, and these things are pretty degenerate. So we cannot really recover this external tensor product. And moreover, there is no functor from strict omega categories to spaces that does work in the intended way. In particular, there's no good functor which takes polygraphs to CW complexes. So instead, what we're going to use is this theory of diagrammatic sets that's developed in this earlier paper. So the name and the idea of diagrammatic sets is taken after a paper of Kapranov and Vervodsky, and this is actually the famous paper which contained a false statement that strict infinity group was model or homotopy types. So that could be the reason why this idea of diagrammatic sets that was in this paper has not really been taken up by anyone else that I could see. So part of this work was about seeing where we can get with it. So one way of seeing the diagrammatic set is that it's a pre-sheaf on some category of shapes of high categorical diagrams that's particularly rich. So it's more complicated than most of the shape categories that people consider, and in particular, it includes the category of globes, the category of simplices, the category of cubes with connections, the category of this category of positive operatives and contractions that Marek Zawodowski has been working on, but it also contains many more shapes. And the reason why this is useful, I wanted this to be a context for high-dimensional rewriting or rewriting in higher categories, which would kind of fulfill a similar role to the theory of polygraphs, if people in the audience are familiar with it, but be also sound for this homotopy interpretation in a way that the theory of polygraphs being based in strict high categories is not. But most conceptually, you can think of the diagrammatic set as being a notion of directed space, which has a combinatorial model of directed cell. In the next few slides, I'm going to give you the only few definitions that I'm going to give in this talk, the only precise definitions. So the main idea is this, kind of a typical operation in combinatorial topology is to take a cell complex and then take its phase set. So we forget everything about a cell complex except the fact that certain cells appear in the boundary of other cells. So for example, here the picture on the right depicts some a cell complex structure on the disk, on the topological two-ball, and the picture on the left depicts the Hasse diagram of its phase set. So we got a top two-cell top that's got two 1 cells A and B in its boundary, and then we've got two 0 cells 0 and 1 that appear in the boundary of both A and B. When we take a high categorical pasting diagram, we can do a similar operation. We can take its oriented phase poset. It's supposed to be a pasting diagram in a two category. We do the same thing, except now we remember which cells appear in the source and which cells appear in the target or input and output of another cell. These are going to be these face posets with an orientation are going to be our basic combinatorial objects. This is heavily influenced by this work by Richard Steiner, the algebra of directed complexes. So given a finite poset P, we can take an orientation on the poset to be an edge labeling of its Hasse diagram with pluses and minuses. And then if we take a finite graded poset in which every element has a kind of given dimension, given by how many elements are underneath it in any kind of maximal downward chain, we define an oriented graded poset as being a finite graded poset with an orientation. And just from this structure, we can give combinatorial definitions of what the input and output boundary of a closed subset is by taking the so here plus is output, minus is input. So for example, we take this set to be all the n-dimensional elements in U that are only covered by elements with orientation plus. Like all the elements that cover it are, if it's in the boundary of another element, then it's in the output boundary of that element. And then to obtain this, the whole boundary, we also add all the elements that are not covered by any, that are not in the boundary of anything that's got dimension higher than n. And then we can take the whole boundary to be just the union of the input and the output boundaries. And then we identify a special class of a closed subset that we call molecules after Steiner, which are the closed subset that somehow combinatorially decompose as a kind of high categorical composite of atoms which are closed subset with the greatest element. So we say that something is a molecule if either it has a greatest element, or it splits into two, it splits non-trivially into two molecules as the union of two molecules whose intersection is exactly the n-dimensional output boundary of one and the n-dimensional input boundary of the other. And then we identify a special class of molecules, which are the ones with spherical boundary. And we say that a molecule has spherical boundary if the intersection of its, for all k smaller than the dimension n of U, the intersection of the output k boundary and the input k boundary is equal to the k minus 1 boundary. So I'll give you an example in diagrams. These are all pasting diagrams in two categories. Here, the first two have spherical boundary, but this one does not have spherical boundary. And really, the intuition is that the boundary of these two is a circle, whereas the boundary of this one, it's not. It's a wedge of two circles. And then we say that an oriented graded poset is a regular directed complex if for all its elements, first of all, we ask that their closure has spherical boundary. We ask that each of their input and output boundaries is a molecule. And furthermore, we impose this condition, which is like the globularity condition that one has, whereby taking say the input boundary of a boundary of X is the same as taking the codimension 2 boundary of X. And then we can introduce a notion of map between these two things as a function that satisfies, that's just compatible with all these boundaries. And we can form a category of regular directed complexes and maps. And these maps have an orthogonal factorization system. And one can prove just from this condition that a map that satisfies these things is going to be an order-preserving map of the underlying posets. So what we can prove is that the underlying poset of a regular directed complex in this sense is the phase poset of a regular CW complex. In regular CW complexes, it's often said that CW complexes are not completely combinatorial objects, but regular CW complexes are combinatorial objects in that they can be uniquely reconstructed up to a cellular homomorphism by their phase poset. So in particular, if we take a regular n-dimensional atom, its underlying poset is going to be the phase poset of a regular n-ball. So we can see this as a kind of combinatorial model of an n-ball, which means that we can take n-dimensional atoms as combinatorial models of directed or oriented n-balls. So now we take this atom symbol to be the full subcategory of this category of regular directed complexes on atoms, and we define a diagrammatic set to be a pre-sheaf on this. So this category of atoms and maps of atoms is our shape category that I was talking about earlier. And as I said, this contains lots of other shape categories as full subcategories. So now on to the monoidal structure. So if we have two orientated posets, we can take their Cartesian product, and then we can give it an orientation, as in the tensor product of chain complexes. What does this mean? There's basically only one good way of giving an orientation on the Cartesian product, and it is by, if one kind of covering relation comes from P, then we take the same orientation as in P. If the covering relation comes from Q, we take the orientation from Q, but we flip it depending on the dimension of the element of P that this is tensored with. And if P and Q are regular directed complexes, this Cartesian product with this orientation is actually also a regular directed complex, which we call the gray product of P and Q. And this is part of a monoidal structure on this category. This restricts to atoms because the Cartesian product of two posets with greatest element also has greatest element. And then we extend this along co-limits to all pre-sheaves on atom. And this gives us a monoidal structure, actually monoidal biclose structure on the category of diagrammatic sets. So I say biclose because this product is actually not a symmetric product. It's non-symmetric. So now this gray product on diagrammatic sets is it's not a Cartesian product again, but it is semi-Cartesian. That the unit object is the terminal diagrammatic set, which is the point. So this is enough to have that the gray product of x and y is fibered over both x and y, because we can project away both of them, and this allows us to mimic the definition of this mesh product and have a Gray's mesh product of pointed diagrammatic sets, and that's going to be also part of the monoidal biclose structure and pointed diagrammatic sets. So now there is a nice geometric realization of this category of atoms, or which extends to a nerve and realization pair between the category of diagrammatic sets and the category of spaces, and that also lifts to a pair of an adjunction relating pointed diagrammatic set and pointed spaces. So in the earlier paper, I was able to show that the nerve of a space, that this nerve functor is kind of homotopically faithful in the sense that it's got a kind of left inverse on the homotopy category of spaces. So this is one but I strongly suspect that this can be made into a Quillen equivalence for some model structure on diagrammatic sets. I still haven't gotten around to that. But here we're just going to be thinking of this realization. So we have that, we can prove that the realization of diagrammatic sets does send gray product to Cartesian product. And the realization of Ponte diagrammatic sets does send smash products to smash products. So this kind of solves one part of the connection that we were trying to make. Now, the bulk of this paper, and I'm not going to show you any of the technical details of it because I don't think I can reasonably talk about it. It's mainly a lot of combinatorics. Is the definition of adjunctions that relate diagrammatic sets in prose. That's the easy part. But there is a quite non-trivial adjunction relating diagrammatic sets and gray categories, and that's what most of the technical work is for. So overall, I get this, in the paper, I get this big diagram of adjunctions. That's not a commutative diagram in particular. If we follow this chain, and we follow this chain, we get two different adjunction between diagrammatic sets and strict braided monoidal categories. So the functors that are important here are, so there is this, well, actually I don't relate diagrammatic sets in prose directly, but there's some intermediate notion that I'm not going to talk about. But the point is that this right adjoint from prose to diagrammatic sets is full and faithful. So it allows us to really embed prose into diagrammatic sets, and in particular pointed diagrammatic sets. We have this G, which is the way that we're going to get a gray category from the diagrammatic set. And well, we've got this U3, which is the composite of this left adjoint and this right adjoint. So it's not an adjoint functor from props to gray categories. The important thing about this functor is that it's a pseudomonic, which means it's essentially injective, which means that given a gray category that is in the essential image of this functor, we can uniquely reconstruct the prop that it comes from. So the main theorem is this. Have this diagram of functors. On the top, we have the external product of probs, and then we include probs into gray categories. And at the bottom, we have this kind of embedding of prose in pointed diagrammatic sets. Then we take this mesh product of pointed diagrammatic sets, but there is a little catch. On the second factor, we actually have to reverse the direction of all cells before taking this mesh product. So, but still is a mesh product. So we get this mesh product, and then we have this functor which goes from diagrammatic sets to gray categories, and these two paths commute up to natural isomorphism. So because this is pseudomonic, it means that at least on the image, on the image of this path, we can actually lift this G to a functor to prob, limited to things that are actually mesh products of prose. So in this sense, we can compute the external product of prose as factoring through this mesh product of pointed diagrammatic sets. So if I have still a few minutes, I'd like to give a little bit of an intuition about why this works. How long do I have?
10 minutes.
Okay, great. So I'm going to show you some pictures of what these gray products look like. Let's say X, Y are just diagrammatic sets. Now, first of all, we have a copy of in the gray product of X and Y. We have a copy of X on top of each zero cell of Y, and we have a copy of Y on top of each zero cell of X, because the model of a zero cell is the unit for the gray product. So the first kind of non-trivial things we obtain are by taking the product of one cells. So one cell product, one cell is a two cell, which looks like this in diagrams. So the way we can see it is that here we have A on the fiber of Y minus, and here we have C and the fiber of X minus. And kind of this two cell somehow pushes C through A from bottom left to top right, and A through C from top left to bottom right. And this idea of pushing things from in these two directions shows up in all kind of gray products pictured in diagrams. So now we have a two cell with, say, n inputs and m outputs in X, and a one cell in Y. We get this picture for phi tensor C is going to be phi tensor C is going to be a three cell, which we can see as a rewrite in two diagrams. And again, here we have phi on the top left, and here we have phi on the top on the bottom right, and phi tensor C kind of pushes phi through C from here to here. And the same thing on the opposite case of A tensor psi. Here we have psi on the bottom left, and it's pushed by A tensor psi to go through A to the top right. Now, if we take phi tensor psi, it is going to be a four cell. So we can see it as a kind of rewrite of rewrites. And so in the input of this, so here we have again, we have a kind of this copy of phi, we have a copy of psi on the bottom left and a copy of phi on the top left. And then we push, and on the top, we first push psi through to the top right, and then we push phi from the top left to the bottom right. Whereas in the output, we do the same thing in the opposite order. First, we push phi to the bottom right, and then we push psi to the top left. And here I picture them as having just two inputs and outputs. And actually, in this case of where everything is two in and two out, some of you may recognize the Zamo logic of tetrahedron equation. Now on to smash product. So what happens in the smash product is that we take the gray product and then we declare that every cell in the fiber of the point has to become a degenerate cell on top of the point. And we're going to picture degenerate cells with dotted wires and dotless nodes. So for example, in phi smash C, we have the picture of before where phi slides through. But now supposing that X and Y have a single zero cell, so everything is in the fiber of the base point, everything gets quotiented out, so it becomes degenerate, except these intersections of wires of phi with wires that come from X with wires that come from Y. So we get that phi tensor psi C becomes this kind of rewrite from something which contains these n non-degenerate two cells into this thing that contains m non-degenerate two cells. And the same thing with X, with one cell in X and the 2 cell in Y. But here we have this funny thing that the order gets inverted, because here A tensor psi actually has Q 2 cells in the input and P 2 cells in the output, which is the opposite of psi, and that's kind of where the need to take the opposite comes from. So just to come to that to that bialgebra equation, we can compute some cells in the smash products of the theories of monoids, which is going to give us a presentation of bialgebras. So here we get a one cell in X and Y corresponding to the unique sort of monoids of these theories. We have a 2 cell corresponding to the monad multiplication, and a 2 cell corresponding to comonad multiplication in Y. This one gets reversed, so they both actually have 2 inputs and one output. Now, one tensor 1 is the only non-degenerate 2 cell in X smash Y. So now we're going to picture 3 cells in X smash Y as being kind of 3-dimensional string diagrams that can trace the history of these copies of the unique non-degenerate 2 cell. So if you take this multiplication tensor 1, again, we have this picture of this multiplication getting pushed through this wire. And we see that as it gets pushed through, these 2 intersections become one intersection. So we get this picture in 3D of these 2 dots becoming one dot. If we take one tensor delta, this co-multiplication, again, we have this thing pushed through, but now it's one dot, one intersection that becomes 2. So we get this one dot becoming split into 2 dots. And then if we take this mu tensor delta, what we get is this picture of first we push this one through, and this intersection becomes 2, then this intersection becomes 2, and then we push this diagram through. So these 2 intersections become 1, and these 2 become 1. On the other side, we do the opposite thing, where we first push this one through, so these 2 become 1, and then we push this one through, and this 1 becomes 2. Picture this in 3D, we do get that bialgebra picture. And if we put back, if we make this, if we trace also the history of these dotted wires as surface diagrams, and we rearrange the diagram a little bit, we do get that intersecting surfaces picture. So this is how this is kind of comes up. So I'm almost finished. I'm just going to give some observations that. So this is so far. I hope I've given an idea of how one can recover this tensor product of prose from this mesh product. However, one thing that we can say is that this realization loses some information. What we get here is actually an oriented 4 cell with an input and an output. It just fixed, it shows an input and it shows an output. But when you realize this as a prob, this becomes an equation. So we're actually losing information. Now, because this nerve of prose is full and faithful, we can actually replace the nerve with any diagrammatic set whose realization as a pro is isomorphic to the original pro. And so, for example, we can, because we can, in diagrammatic sets, we can have oriented 3 cell. We can work with a presentation of a monoidal theory, which has oriented 3 cells and has nice computational properties. And if we work with presentations which have interesting oriented n cells up to n, then the mesh product is actually going to have oriented k cells up to 2n. So we're going to have a lot of high-dimensional data. And the idea is that given 2 presentations of 2 pros, this mesh product not only produces a presentation with oriented equations of their tensor product, but it also produces systematically some high-dimensional coherent cells, or what can be called the oriented homotopical syzygies or homotopical generators, whatever people want to call them for this presentation. So for example, if we have a presentation of the theory of monoid that contains these directionally, these would be associativity and unitality equations. We get a presentation, then taking this mesh product of X with itself is going to be a presentation of the theory of bialgebras, containing, for example, that 4-cell that I pictured earlier. And this presentation is going to contain, if you approach it from a rewriting perspective, it's going to have some new critical branchings that do not come from critical branchings in the factors. For example, we have this new critical branching, where here we can either do an associativity move or we can do a bialgebra move. But now in this mesh product, we're also going to have a 5-cell given by this associator 3-cell and the multiplication 2-cell. And this is going to be a kind of coherence cell that exhibits confluence at this critical branching. Like this. This is going to be its input and this is going to be its output. In addition, we're also going to have some high-dimensional cells, which we can see as higher dimensional oriented syzygies that exhibit confluence to critical branchings of syzygies. So now, a question that I have is, if we start from presentation with nice computational properties or nice homotopical properties, do we obtain presentations of the tensor product which are nice in the same sense? For example, we start with convergent presentation, can we extract systematically and synthetically or compositionally, can we extract nice presentations of the tensor product? And to really conclude now, another direction we can take this is to say, well, we're now thinking about pros and props and monoidal theories and braided monoidal theories. And we can see these as low-dimensional objects. But the thing is, in diagrammatic sets, we're not constrained to having to only think about presentations of low-dimensional things. They can be a context for thinking about presentations that have oriented generators in an arbitrary dimension in a way that's homotopically sound. And in particular, we can generalize this idea of monoidal theories and braided monoidal theories to k-triply monoidal n-dimensional theories. So there'll be theories that have interesting data up to dimension n, and that are also kind of k-fold directed loop spaces. So remember, monoidal was a loop space, braided monoidal was like a 2 space, but we can have interesting things and higher up. And the point is, if we take this mesh product of an n-triply monoidal theory and a k-triply monoidal theory, we get an n plus k-triply monoidal theory. And we recover the fact that the tensor of monoidal and monoidal gives braided monoidal. And in particular, we can consider symmetric monoidal theory as being something that's stable in the sense of stable homotopy theory. So it's k-triply monoidal for each k. And in this case, if we take this mesh product to symmetric monoidal stable theories, then we are going to get another symmetric monoidal theory. And this is, I think, the real kind of reason why props do have a closed structure, that they do have a tensor product, but pros and props do not have an internal tensor product. This is the very last slide. Thank you. I'm sorry I went a bit over time.
No problem. Okay, thanks a lot. Very nice. Are there questions or comments?
I have a very vague question, as usual.
Yeah, please go ahead.
Do not see who the speaker is.
This is Andy. I don't know if you can see me. Where's my camera?
Yeah, now I see.
Okay, terrible camera. I'll turn it off. Look. So that's a very nice presentation for products. Can I suggest something completely crazy? Could you see any way of doing it for extensions? I mean, like twisted tensor products. I mean, the idea of a fibration of series occurs like, I guess you can see associative, commutative, and Lie in a fibration. Can you see any way of getting some twisted smash product or model for a total space given the base and the fiber? I mean, given two presentations, you're constructing a nice presentation. That's how I'm thinking of it.
So I'm afraid this is one of those points where I show my ignorance as a homotoppical algebraist. I do not really know what many of the things you mentioned are. So I would love you to tell me about them.
Okay, just start with something. So you have a tensor product of something which is like analogous to a Cartesian product.
Yes.
Just think of an easy way of thinking of it. Can you think of some way of twisting it so you get something analogous to a semidirect product? That would be the first little step.
Yeah, I've never thought about it, and
Okay. It wasn't meant to be a very a very obvious question. Yeah, thanks.
I definitely like to talk about it.
More questions? Well, I have one. Can you explain a little bit more about this up arising? Because it looks a bit strange, like in places where you would expect it something braided monoidal, instead you get some bialgebra stuff. I mean, it appeared somewhere and you explained the up, but maybe you can elaborate a little bit on it.
Yeah, so again, so the thing is that when we somehow every time we take a gray product, or rather a smash product with the one cell with the one cell of some other diagrammatic sets, we're doing a kind of suspension of the cells of the two factors. But what happens is that because of this tensor product of chain complexes orientation rule, what happens is that if I take the smash product, let me go. Yeah. What happens is that if I take the smash product with a one cell in the second factor, then for two cell in X, then the orientations of the boundaries of phi from X are preserved in the smash product. So the input of phi in X is going to go into the input of phi tensor C in X smash Y. So that's why here in this mesh product you see that A1C to ANC are in the input of this, whereas B1 to BM are in the output of this. But now if we take the smash product of a one cell in X with a two cell in Y, now we've got a one dimensional thing here. So by the rule for taking for the boundary of a tensor product, the orientation of the boundary of psi gets flipped. because we get a factor of -1 to the dimension of A, and A is one-dimensional. So this is why here we get psi as having d1 to dq, so its outputs appear in the input, and its inputs appear in the output here. On the other hand, when we do the tensor product of props, what we do is first we build a free prop obtained by taking a kind of a co-product of copies of the two factors indexed by the sorts of one on one side and indexed by the sorts of the other one on the other side. So in particular, for every sort of one prop, we have an actual inclusion of the other factor into it, and in particular, at every sort, the kind of the orientations of the operations of the second prop are preserved by these inclusions. So in the tensor product of props, we do not have this orientation flipping behavior. So if we factor it through this mesh product, we have to kind of put in, we have to flip things by hand to recover the correct orientation. I do not know why any of this happens except from explaining you what's technically happening.
Okay, thanks. But does it mean that when we usually think about, well, first monoidal structures and then braided monoidal, and then you go further on to E3 and E4 and so on, that we could also think of those as first, well, and instead of braided monoidal, you get bi-algebra somehow. I mean, what if you look at the periodic table, how can I put bi-algebras, and what are the higher versions of those? What does, well, I don't know how to ask a good question, but it looks, I don't know. After bi-algebras, what do you get? I mean, if you continue just...
So here so here bi-algebra is obtained as as a smash product of, let's say the theory of monoids with itself, actually. Well, if we see there's presentation picture. So when you say what happens further on, do you mean by iterating smash products?
Yes.
So what is going to happen is so if we do it once, we get monoids mesh comonoid, if you want, because of this flipping. But if you keep flipping, then you get other factors which are still going to be presentations of monoids or of comonoids, because it's an involution. So if we do it once more, we're going to get a presentation of the prop of bi-algebras that are commutative but not co-commutative. If we do it once more, we're going to get, because we're going to stabilize in terms of presentations, like there's nothing more beyond symmetric, we're going to get the prop of commutative and co-commutative bi-algebras, and then nothing else.
Okay, so at level 4, for example, you would get something like braided monoidal internal to braided comonoidal or something.
You would the level of the point space would just let you would get just 3 times delooped, so like threefold loop spaces. I'm not sure about the internal picture that you have in mind.
Well, I'm not sure myself. Okay, thanks. Now there's a a question in the chat from Michael Batanin. He asks, did you consider product of globular operators?
No, and at this moment, I would not know how to start precisely because I said most of these proofs rely on these sort of very combinatorial constructions that I do not know presently how to generalize from just set operands to globular operands. I do not see any reason why it's in principle impossible, but I think I would need to know much more about globular operands to even get started.
Any other questions or comments?
I have perhaps a small question on the category of diagrammatic sets. Is there some kind of model structure on it?
So I think, I know how one should put a model structure in it. I haven't gotten around to trying to show that it gives a equivalent junction with the category of spaces or anything. But well, there is a very natural kind of notion of what generating cofibrations and generating acyclic cofibrations should be in diagrammatic sets, and that's that's precisely the inclusion. I said I have these models of directed n cells, so the cofibration should be just the inclusions of boundaries, and acyclic cofibration should be inclusions of boundary minus one cell in the boundary. So from there, I think just by sort of abstract model category theory, I can probably obtain a cofibrantly generated model structure on the category of diagrammatic sets. Again, probably some of the work towards establishing equivalent equivalence has already been done, but not. Some of the work is still lacking.
Thank you. Okay, can I ask you a second question?
Yes.
About the relationship between your Smash product and the Bodman-Vogt tensor product. Is it possible that if one applies these reflecting functors to go back to props, that you get actually some kind of cofibrant resolution of the Bodman-Vogt tensor product? Say, by inverting all cells you get, does this induce some kind of symmetric monoidal structure on props, which would be better behaved than the Bodman-Vogt tensor product?
So I'm not sure I understand how this can be done internally to the category of props. So unless you're but because this kind of this kind of high information is really it's really trivialized by this functor, which takes me from diagrammatic sets to gray categories and to props. But maybe I just don't quite understand the terms of your question.
So maybe it's also not well posed, my question. But somehow you see that there is this gray tensor product the symmetric version of the gray tensor product of two categories, which gives you
okay.
which gives you a three category, I think, or nowhere. So you have this gray tensor product of two categories, and
Yes.
I of course there is this lax version on omega cat, on strict omega categories.
Yes.
But somehow I got the impression that your smash product is not exactly the same thing.
No, so I have a functor which goes from diagrammatic sets to strict omega categories. Actually, yeah, I do not have a complete proof of the fact that that this takes gray products in this sense to gray products in omega categories, but it is definitely true. And if it is not true, then something is very wrong with strict omega categories. But so in this sense, yes, this gray product is the same as that one, well, minus the problems that come from strict from the context strict omega categories. So sorry, now I've lost the and
yeah.
so
yeah.
Well, if you include prose into diagrammatic sets, then take the gray product of diagrammatic sets, and then actually go back to prose or to two categories through that adjunction. Then in that case, yes, I can say that what you will get is actually the lax gray product of the original two categories.
Okay.
Because the fact that the two coincide is proven in low dimensions. It's just in high dimensions that becomes trickier.
Thank you.
Any more questions? Well, then maybe we should thank Amar again. So thanks a lot.